All right, so today we're going to be talking about a bunch of different properties. So you'll get a sheet to help you with some of these, but these first three you're going to want to write down in your notebook. So these first three properties are the names aren't terribly important, but they're things that will help you get names for things you already know how to do. So we're going to be talking about the reflexive property, the symmetric property, and the transitive property, and what exactly do they mean. So we'll start with the reflexive property. So the name basically means something is equal to itself. You may be wondering, why in the world do we need a property like this? Well, it's more to help with things, for example, like if I'm talking about a line, we talked about how you name a line. We said you just need 2 points that are on the line to name it. So I could name this line AB, I could name it BC, or I could name it AC. So the reflexive property allows us to say that line AB and line BC are the same thing, because something equals itself. AB and BC would be the same because they're the same line. So that's when it's going to become useful. So like if you need to change names. So when we're working through a proof, I'll go back up and look at one of our examples from yesterday. So an example like this, you have to match this prove statement exactly. So exactly what it says here, meaning if it's backwards, if it's different letters, it's not correct. You need to get exactly x equals -5. So having it backwards like this would not be appropriate. So these properties are going to be to help you get exactly what you need to have in order to be correct. So that was the reflexive property, would allow us to change names. So if in that example up above we had somehow gotten to a z, we are allowed to say that z and x are the same, if we can show that. Symmetric property is another thing that you already know, but you probably didn't realize you knew. It just means that I can flip sides of the equal sign and nothing changes. Meaning, if I have x equals -5, that's the exact same thing as saying -5 equals x. They're interchangeable. But you do need a property in order to say that. Because again, if it doesn't exactly match what is said here, then you're not done yet. So this here would be backwards, and we would need to use the symmetric property to make it the right way in order to be completely done with our proof. So flipping sides of the equal sign doesn't change anything. That's all that property says. Now, the transitive property is something that you, again, already know what it is, but it's just a way to explain what you know. So I like to use the example with people because it makes a little bit more sense in my brain that way. So let's say, for example, I have 2 people here. I have Mike and I have Sally, and they're the same height. So here's Sally. And then Sally goes and stands next to Joe. So here's Sally again, standing next to Joe. And she's the same height as Mike, and she's the same height as Joe. What can we say about Mike and Joe in terms of height? Well, we would be able to say that they're also the same, because if they're both the same height as Sally, then they'd have to be the same height as each other. That's the transitive property. It just says that if I have 2 things equal to the same thing, then they equal each other. So mathematically, if I said A equals 5 and B equals 5, then I'm allowed to say that A must equal B because they both equal the same thing. So that's the transitive property. This just allows us to connect different ideas together. So if I had to put it into words, I guess you would say it connects ideas together. So those are the 3 big properties that you're going to use quite a bit. No matter what type of proof we're dealing with, you'll probably use one of these, particularly that transitive property. For some reason, that one shows up a ton. But on your sheet, you have a whole bunch of different postulates. So postulates is just a name for a type of rule. So this just means a type of rule that we're talking about. Now, all of these rules are things that you should already kind of have an idea about, but they're just putting them into words. So First one we'll talk about, the two-point postulate, which just says that if I have any 2 points that exist in space, there's only one line that can go through them. Remember what we said is that in geometry, every line has to be a straight line. So when it says that there's exactly one line, it means a straight line that connects those 2 points. So going from A to B, there's only one way for me to make a straight line through those points, no matter what. So there will never ever be a point where I can make a second line that's not the same as this purple one that connect those 2 points. This also works in reverse. If I have a line that exists in space, on that line there must be 2 points. I might not know what they are, but they do exist out there somewhere. All right, intersection postulate. What it says is that if I have 2 lines and they cross at any point, their crossing point is exactly 1 point. It can't be any more than that, can't be any less than that. So if I have 2 lines and they have to cross at a point. Moving on, the 3-point postulate. If there are any 3 points that exist in space, just 3, then there is one plane that connect all of them together. Only one. So it's kind of like the same idea as this. 2 points make a line, 3 points make a plane. And it again works in reverse. If I have a plane that exists in space, then there are 3 points that land on it. All right. The plane line postulate. If 2 points lie on a plane, then the line containing them lies on the plane. So if I have a plane that exists out there and there are points on it, 2 of them, then the line that goes through there, so that's using this rule here that if I have 2 points, then a line must go through them. This line has to be on the plane. So if 2 points are on the plane, then their line is 2. And finally, the plane intersection postulate, which says that if I have 2 planes and they cross each other, they cross at a line. So all of these different postulates are just things that you already know and that you probably just never really took time to think about. So going back, if I have 2 points, one line goes through them. If I have a line, it has to have 2 points because that's the reverse of this idea. That's the symmetric property of that rule. If 2 lines cross, they cross at a point. If I have a plane, it has 3 points on it. If I have 3 points, they lay on a plane. If there are 2 points that are on a plane, then their line has to be also. And if I have 2 planes that cross, they cross at a line. All right, which of the statements cannot be assumed from the diagram? So looking at this picture, can we assume that A, B, and F are collinear? So let's take a look. We have A, we have B, we have F. I see a line going through them. So that can be assumed because there's a line that goes through them. E, B, and D. E, B, and D. Is there a line that connects those? No, there's not. So we're going to hold on to that one and just check the rest. AB is perpendicular to plane S. So AB, the line, is perpendicular to plane S. Remember, that means it makes a 90-degree angle. So if it's a perpendicular line, that would mean that I should see a 90-degree angle, which I do, so that one's good. CD is perpendicular to plane T. So CD, perpendicular to plane T. This one's a little trickier, but it is true, because since CD lays on this plane, this one here, and we already have this 90-degree angle that exists, then I'm allowed to assume that this also would have a 90-degree angle using that transitive property. And finally, AF intersects BC at point B. We can see that from the picture right there. So that one has to be true. So this is the only thing we can't assume because there is no line that connects them.